Hello once again, and thank you for joining our webinar on introducing KumoRFM-2. I'm Katie Jovanovska, and I will be your host today. In this webinar, you will have the opportunity to hear from Jure Leskovec, professor at Stanford and co-founder and chief scientist at Kumo, Disha Dubey, data science lead at Kumo, and Vid Kocijan, machine learning engineer at Kumo. In this session, you will learn how to break down the key ideas and innovation behind Kumo RFM2, understand benchmark results and what they mean in practice, and see real workflows demonstrated end-to-end and explore use cases across sales, marketing, and fraud. Before we begin, please remember to use the Q&A section to ask any question throughout the session, because at the end, we will dedicate time to answer your questions live. Thank you again for joining. Now I'd like to invite our co-founder, Jure Leskovec, to begin this workshop. Jure, over to you.
Thank you, Katie. Hi, everyone. Super excited to be here and share with you what we built at Kumo. So the motivation for what we are doing is that foundation models have really reshaped AI in the enterprise for all kinds of use cases. But if you think about it, there is a humongous gap, right? That basically there is a missing data modality that today's AI approaches are essentially not considering, right? We have zero-shot pre-trained models for natural language, allow us to talk to the models, reason, do content generation, and things like that. We have really good vision, audio, video models that allow us to do computer use. We have coding models that do reasoning and mathematics. But what is missing in this picture of different data modalities are the large-scale models that are able to reason over structured tabular data. And the reason why this structured tabular data is so important is because most valuable data in the enterprise lives in this type of structured tables, right? Every organization, has a set of customers, has a set of transactions, has a set of orders, has a set of products. And this data lives in a structured form together with images and text and all kinds of data, and is interlinked in a sense that there are pointers where an ID in one table points to an ID of another table, right? So when we have an order has a user ID, so we know which user ID plays that particular order. And being able to reason and make predictions, inferences over this data is super important because it allows us to make accurate decisions that affect the business. So what do I mean by decisions? By a decision, I, for example, mean to decide what products to recommend to a customer so that they will be happier, they are going to find the thing they're looking for and order or consume more. And we see that even 1% increase in, let's say, in accuracy of these recommendations can lead to a large gain in profits. Similar, if you think about demand forecasting, where we are predicting, let's say, the likelihood of a delayed delivery, even a small increase in accuracy there can help us lower the inventory cost and optimize the business. And similarly, right, there is always fraud everywhere. And if we can estimate the likelihood of, let's say, a transaction being fraudulent, account being fraudulent, this means we can significantly lower the losses, right? So even small increases in accuracy of these models that are reasoning over this type of structured tabular data historically are very important. And if you think about how has this been approached so far, or how are we dealing with this type of structured tabular data, we are basically stuck with machine learning. And why is this problematic? It's problematic because fundamentally it hasn't changed for the last 20 plus years, right? Data scientists, machine learning engineers who take this richly structured relational data, and then they would do a bunch of ETL, feature engineering, training data set generation, validation, model training, model validation, putting models in production, building these feature stores and feature pipelines to finally get these predictions. And when we look in the industry, it takes about 2 data scientists per model. So you need a lot of human work to do this. It takes very, very long, usually about half a year to develop a single model. It's very expensive, can be millions of dollars per use case. And most of these models actually never reach production. They never get used in practice, but they get dropped, they don't perform well, and so on. And because of this manual feature engineering and this pipeline maintenance and so on, just the maintenance cost of these models is very, very hard. So what we have developed is Kumo RFM stands for a relational foundation model. Relational meaning it's a purpose-built neural network architecture that can reason over structured relational data. So, and the point is that this is a pre-trained model that can adapt to any database, any schema, any set of different tables and outperforms strongest supervised models, no feature engineering needed, and it's very scalable. It can scale to 500 plus billion rows, no problem, right? So even the largest enterprise data can be dealt with this model. So, and you could say, oh, is this just another LLM? But it's not an LLM because the key insight is that your database is not a document. You cannot textify your table or your database, put that into a large LLM and expect it will do well. You actually need a purpose-built and purpose-trained neural network architecture that can reason over these types of data. So foundation like the large language models are not able to do this. We cannot train them because their attention mechanism is inherently sequential, but we need to invent new kind of neural network architectures, new kind of training recipes to be able to train. So, it's not obvious how to do this, but this is the core innovation of what we've done at Kumo, is that inside that the database is not a document, it's not a sequence of tokens, but it's actually a graph of interrelated tables, and that the attention mechanism needs to be extended to be able to attend across different columns, across different rows, and across different tables. And through that generalization of the underlying architecture, as well as a way to pre-train this architecture in such a general way that it can reason independently of the underlying data and underlying schema, as well as be adaptive to any predictive problem, is the key hard part. But once we have this means that now, we don't need to build purpose-built models anymore. We simply ask a question and we receive an accurate answer deterministically without hallucinations. So with this, I would just like to say that basically predictive AI is changing, right? The XGBoost and feature engineering are basically going away. And it's all about building foundation models that neural network that reason directly on top of the relational data natively as a missing data modality in today's AI ecosystem. And with this, I'll hand it off to Disha to actually give you a quick demo.
Thanks, Jure, for the insightful talk on introducing our relational foundation model and sharing the concepts. Now I will cover how this works in action. Let's bring this to life with a predictive AI for sales intelligence use case. So imagine that I'm a sales leader, and at the beginning of the quarter, I'm not just asking simple questions like how many active deals are there, but I'm asking harder questions like which opportunities are most likely to close, or which ones will become bigger wins next quarter, or which one are slipping. Today, sales teams have pipeline visibility through dashboards, CRM views, and reports. But what they don't have is who is actually going to close and when, which deals I should be prioritizing, and why. So what we are going to do here is we are moving from that visibility through dashboards to predictive deal intelligence in minutes. Here's exactly what I'm going to do in the next few minutes. I'll start with a simple question. How many deals do we have today, which are in the pipeline? Then I will ask which ones are likely to close by quarter end. Then what are they even worth for? And then what's going on inside each of these deals? And critically, one of the important questions is why a particular opportunity was ranked high or low. And then finally, how this changes your plan for the quarter. And this entire workflow would happen through a single model, which is Kumo RFM. Let's go to the playground here. So this is Kumo Playground. And before even I start asking these questions on my data, let me show you how we even got here. I've simply pointed Kumo RFM to my sales tables in this warehouse. You can add the tables here using some of these links. Once you would have access to the playground, you'd be able to see how this works. And so what I'm doing here is I just connected to my warehouse. There is no data movement here, no feature engineering. From there, once I do this, Kumo automatically builds a graph of the business, connecting accounts, opportunities, leads, products, the time component of these opportunities. And then what this structure allows the model to learn is it learns the pattern across your entire pipeline, your entire business context. And then once I do this, what I do is I define what I care about in plain language. Let's go there. So this is the chat interface in the playground here. Once I define what question I want to ask, I will simply start typing here in the chat and ask these important questions to Kumo RFM. So for my sales op data set, which had opportunities, leads information, and accounts information, some of the important questions that I will be asking is when a deal would close, what's the average deal size, and why the model is predicting it to be a certain way. So as you can see, I won't be writing any ML pipelines here. I will just be defining my question. And once I have that question defined, I can immediately start asking those questions on top of my data in this chat interface. So now let's actually go ahead and do that. So let's start with a basic question that as a sales leader I would have, which is how many active deals at the start of assuming Q4 2025. All right. So here, as you can see, the model specifies there are 0 deals here. Let me go to my existing chat where I had some answers to show you what was in here. So actually, technically, there were like 49 deals. My quarter is wrong here, so I think I'm on the wrong data set. But once the model will tell you how many deals are there here, the next question, basically, this is nothing new. This is something that your dashboard can give you. This is more of a backward-looking insight. So nothing new so far. Your CRM view would already tell what's going on here. But what we see is typically this is where your traditional tools stop. But with Kumo RFM, you can go to the next stage, which is instead of reporting just the past, you can ask the model more forward-looking questions where you would say, predict which deals out of these will close by quarter end. So that would be the next question as a sales leader I would ask the model. And now when I do that, the model is telling us that none of the deals are going to close in the next quarter. Now, this is the kind of signal that teams usually discover very late in the process. Even if you can see here in the data, even the best deals that are here have a very low probability of closing, which is around 3%. Now, here, looking at this, this isn't just a simple prediction. What this is signaling to is a risk. It's forecasting the risk signal for the sales leader. And basically what it's saying is you're entering the quarter with a pipeline that looks healthy, but is extremely unlikely to convert. So now instead of guessing, we can actually look at this data and we can rank order out of all the active opportunities that we have, which ones are the most unlikely to unlikely to close. And this is how reps should prioritize their opportunities. They should prioritize their time this way, not based on gut, but based on the probability of prediction of closing. So once I have visibility around likelihood to close, the next thing that I would want to do is I would want to rank order these opportunities. So I would ask the question of predict what are some of the top deals out of these which are most likely to close. And I can see the results, the rank ordering here that was given to us by Kumo RFM. And it's calling out that there are these three best candidates here whose likelihood is slightly higher, relatively higher than the other deals that I have in the pipeline. And but even these are under 4%. So this tells you that prioritization alone isn't enough. Something needs to change here. Then once I do this, I want to also take a look at some of these top deals. Let me see what these deals are, like which are these accounts, which sales reps are representing this opportunity, and what kind of, what region is it from. I can get information about these top deals and see that these are all different opportunities represented by different sales reps. And this is basically directly coming from the data that we had shared. It's the business context that you have already provided. So from here, once I understand what these opportunities are, I would also want to connect this to the revenue side of things, which is what's the predicted deal size? What's the predicted deal size of this opportunity, which would give me some revenue aspect, some insight into how big these deals are and what's the best case revenue scenario for Q4. So this will give me visibility around not just the likelihood of conversion for my pipeline, but also getting to the next level, which is being able to forecast the dollars for this quarter correctly. So this is how I'm moving from just the pipeline size to actually real revenue expectation setting for my team. Now, once I understand that, the next thing for me would be to understand and trust the model in terms of what it's predicting, why it's predicting that. So the next thing that I would do is to ask the question around why that specific deal of this opportunity basically is predicted to close, why the model said that. And this deal ranks higher, as we can see here, this deal ranks higher because it's one of the renewal deals. And in the past, we have seen that this has worked well for us. We can see that based on the history of this pipeline, which is coming from the deals history table, based on where it is in the cycle, it is expected to close compared to other opportunities because it's very close to 60 days. And some of the other sales motion signals are also indicating that the likelihood of conversion for this one would be higher. So at this point, what it is doing is the model is not the black box here. What it's showing you is what are these exact signals that are driving these predictions. And at the same time, it's also being cautious and telling you that even though the probability is relatively higher, but it's being cautious that in absolute terms, this probability is still low for this account. So these are having something like this can give these leaders more confidence around trusting these models in terms of what they are saying, why they are saying that, and then this will let you act and not just observe what's happening in your data and what's happening in your business. Now, once all of this is set up, which is I have the visibility around my pipeline, I know the revenue opportunity, and I know what are some of the top deals that I can focus on for this quarter, I would want to step up and move to the planning phase, which is looking at out of these opportunities, which ones are more likely to close this quarter versus the next, or which are more longer term deals here. And for that, I can ask this question, which is, which deals are more likely to close this quarter versus the next quarter? And when I do that, you see that Kumo RFM would run multiple predictive models here. So just to give you a quick sneak peek on exactly what happens here is Kumo RFM would run these predictive models at different time frames, and based on that, it makes an informed decision around why it's predicting that certain deals are more likely to close the following quarter versus this particular quarter. And here, the model shows that almost no deals have meaningful probability of closing this quarter. We saw that. But then some of these opportunities have a high likelihood to move to around 14% probability in the near future, which is the next quarter. So it's giving me an insight that my pipeline that I already have, which is active, is in fact not a Q4 pipeline, it's a Q1 pipeline for me. So understanding all of this, at this stage, what I would do is, instead of committing this quarter, I would basically reset expectations early. And I would focus interventions on some of the top deals that I saw, which are relatively high likely to convert this quarter. And then we'll build a strong quarter pipeline for the next quarter. So going from what deals I have in my pipeline to opportunity sizing those deals, knowing which ones to prioritize this quarter and which ones to focus on the next quarter, gave me this entire visibility around my whole sales pipeline. Now, what you just saw is not a sales-specific use case. What we did here is we predicted an outcome. We understood why. We ranked these opportunities by priority, and we recommended next best action. This is something, even though we saw in sales context, it's applicable everywhere. This is the core pattern of every enterprise decision. And this is what helps you turn your model into a decisioning system. So let's take the same model, but let's see how the same model can be expanded and used in different decision making. So considering financial services or banking context, now here in this case, you would be predicting recommending products to different customers. You would be identifying fraud. You would be identifying how to best engage with your customer. Similarly, in case of marketing context, now in this case, you would be automating campaigns. You would be selecting audience for those campaigns. You would be figuring out what channel to target and how to attribute to different channels. In case of supply chain, you can basically forecast the demand upfront, be more proactive about it. You could forecast supplier risk and preemptively take actions on those. You could also predict the schedules for these different delivery. You could predict the demand for parts. In industrial context, you could basically predict failures upfront before they happen, and this could save millions of dollars for the business. So long story short, same model, same workflow, different decisions. This is what the foundational model gives you. And the key difference here is this isn't just a custom model per use case. What we did was we used the foundational model. We connected the data, and we basically pointed it to the foundational model and got the predictions instantly. All right. So this was the demo, and now I will hand it over to Vid to discuss some of the architectural innovations that we had in the platform and share some of the exciting benchmarks of the foundational model. Over to you, Vid. Thank you.
All right. Thank you, Disha, for this beautiful demo, and thank you everybody for joining. Now, let us take a look behind the scenes and see how this model actually works. But before we can talk about technical details of the solution, let us take a closer look at the problem itself. So, a foundation model for relational data needs to be able to operate on a diverse set of possible input database schemas with multimodal data. A user can, for example, connect their own database, and our relational foundation model needs to be able to make predictions without task-specific retraining. So the model needs to handle arbitrarily connected tables of varying relationship types. In a medical graph, for example, a patient might have one general practitioner, but a long history of past visits. On the other hand, a financial graph will see both regular repeated transactions as well as many one-off payments. Moreover, all of these tables come with a collection of different column types, including numerical, textual, categorical, temporal, and others, each column with its own semantic meaning. But diverse input data is not the only source of complexity. Just like the underlying schemas, tasks greatly differ in their properties. They range from one-off assessments that only require missing value imputation, for example, predicting whether a transaction is fraudulent, to tasks with a long time window, such as forecasting demand. And connecting the two is a Kumo relational foundation model, a system that reads a raw relational database and your task description, and using them to provide best prediction based on the historical data. Crucially, this model is frozen and not tuned. It makes predictions about the future purely by extrapolating from examples provided as part of the input. This not only allows quick generalization to new previously unseen data without any additional training, but also enables responsive interactions and quick answers. Now, of course, the model cannot be trusted without appropriate evaluation, not only on publicly available benchmarks, but also on your own specific task. After all, every task has its own complexities and level of noise, so evaluation on past data is essential to understand which predictions are made with high confidence and which are not. But predictions are not just about accuracy, but also about learnings. So to this end, predictions should be accompanied with explanations, providing insights into why a prediction has been made. This allows not only fast, but also informed and confident decision-making. And Kumo RFM delivers all of this, and we've got numbers to prove it. We have evaluated Kumo RFM on a collection of benchmarks. On the screen, you can see performance on multiple parts of RelBench dataset, a popular academic benchmark for predicting future behavior and entries into relational databases. As for those of you coming from a more commercial background, you might be more interested in results on SOLD benchmark. That's a dataset from an ERP system containing a collection of tasks from real-world business contexts related to sales. And in all of those benchmarks, Kumo RFM on average outperforms previously best models, even the supervised ones. All of these evaluations were done only with in-context learning. The data from this benchmark was not used during the model training. This should go without saying, but it's worth pointing out. Up to this point, and throughout the demo, we have been emphasizing the in-context learning as the means towards faster and low latency predictions. However, sometimes you may prefer to wait longer for the best predictions possible. In such cases, our platform offers fine-tuning on the entire dataset, and fine-tuning can still be used to further boost performance, as demonstrated on the SOLD dataset on the right. But in practice, tasks do not naturally come with predefined training data. In practice, the context data needs to be sourced from your relational database. As already demonstrated by Disha, each query for Kumo RFM can be asked in natural language. But in the background, we translate it to a well-defined and specified predictive query language, which can also be written by an advanced user directly. This allows us to make the remainder of the process reliable and remove any risk of bugs that could sneak in had the context generating procedure been AI controlled. The query provides us with the entity definition, in these examples, item IDs, and the target definition, sum of order prices over the next 30 days. Now, given a timestamp, we can generate labels by moving back in time 30 days at a time and computing the label for each entity for past data. Of course, any input data sampling needs to respect the earlier timestamp as well. We do not want any data leakage. We repeat this procedure, going back in time until we fill the context or exhaust the available history. The computation of this procedure can run either in your local memory or with push-down compute to a database platform like Snowflake, unlocking scalability to massive databases up to 500 billion rows. And the inputs? Well, unlike traditional tabular machine learning, we do not perform any feature engineering. It requires too much manual labor. Instead, we treat the database as a graph, where each row is a node, and primary and foreign key relations define edges. Let me explain this on an example. On the screen, we are trying to predict future behavior of Alice in a database of item orders. To collect data relevant to future behavior of Alice from the database, we sample the neighborhood of this node, Alice's past transactions, Alice's past views, and their corresponding items. And while doing so, of course, we respect the timestamp of the example and only sample rows with timestamps before the anchor time. Taking this further will give us not only Alice's orders, views, and items, but also other people who bought the same items and their past orders, all useful signals for predicting Alice's future behavior. And this is the input that will be given to Kumo RFM for every context example, as well as inputs that are making the predictions for. With a collection of context subgraphs and their corresponding training labels, we have prepared the input context. Kumo RFM will perform the next but crucial step: extrapolate the prediction into the future. And how did we obtain such a model? Well, we needed to innovate in multiple areas required to train a machine learning model, and that would include a novel machine learning architecture. Like most modern neural network models, we rely on transformer architecture. However, as already earlier mentioned by Jure, vanilla transformers are not designed for complex relational data. They're designed for sequences. We therefore introduced this triple hierarchical attention that attends to data at 3 layers. So each cell in the database would attend to its corresponding rows and columns in the same table, allowing reasoning at the level of the row and at the level of the column. At the second level, rows would attend to each other as defined by the connections between foreign keys and primary keys. This allows inter-table connectivity and reasoning about the database structure. Finally, the third layer of attention is what operates at the level of examples, allowing different examples to connect to each other and enabling in-context learning. And these 3 blocks of attention are stacked interchangeably, creating this expressive model architecture that can capture correlations at the level of features as well as database structure. This, when trained on various publicly available data as well as synthetic data, is what unlocks an amazingly performant model, not just for public benchmarks, but also for proprietary data. And as of now, Kumo is the only relational foundation model trained end-to-end. This is just a step in a long journey. To describe where we are headed next, I would like to give word back to Jure to open the talk.
Yeah, we are extremely excited about this line of work and this line of innovation, because only through this relational information, the full richness of the data can be captured. The second important thing is that what you saw here is that the same pre-trained model can be applied to any database and can answer any predictive type question, either formulated in natural language or formulated in the domain-specific language, which we call predictive query language. This is very important, especially if we think about either humans or agents trying to reason over this type of data to make inferences in order to make decisions. So this becomes very powerful if you think of having a sales agent, a fraud detection agent, a customer support agent, because for example, customer support agent needs to decide what offer to give, what discount to offer, how likely the person is going to churn, and all these type of decisions that then change how it's, let's say, communicating with the customer. Another important thing is that the data is inherently relational, both private data as well as public data. And through this relational model, it is able to significantly enrich the underlying data by connecting it to other data sources, right? You can think connecting product catalogs to your ERP, SAP data, connecting to the external news source data, to the weather data, to the economics data, and things like that, right? All this is easily possible with this relational approach that we have developed. And this becomes very important because the key to making good decisions in the enterprise is about understanding the future and estimating the effect of those decisions on the future. And with this relational approach, as I said, we can basically integrate many different kinds of data, support many different predictive questions that require reasoning over this type of data, all in real time at massive enterprise scale. So I think with this we are done. If you would like to try these things out and play with them, you can go to our website, kumo.ai. We also have a white paper called KumoRFM-2 that is available on archive as well as on our website. And our model is freely accessible through a simple API. You basically can download the SDK, use your own data, and start using it. What we are going to do next is we are going to move to the Q&A session. And my friends here and myself are going to go through questions and try to answer them. Please use the Q&A section or capability of Zoom, and we can have the discussion there. And I think, Disha, you are going to start.
Yeah, so I saw one question from Dimitri, which is how do you eval the model against my own company's data? If the performance is below the desired threshold, is there any way to fine-tune the model? Yes, so I'll start with this one. Dimitri, yes, you can evaluate the model on your company's own data. A common starting point would be you start with Kumo's pre-trained relational foundation model. It will give you a very fast baseline on your relational data. It should work great, but if you see that the performance is below your desired threshold, then what we can do is you could use Kumo's foundation fine-tuning platform to train a model on your specific task. And then it could be a model on your data or a specific task and try to optimize on that case and get the answer. So we have these both kinds of offering. Start with relational foundation model, and then if you want that extra squeeze of performance, go to the fine-tuned version of the model.
Thank you, Disha. Maybe I'll take one question, which is about the model itself and its performance. So we have validated the model on external private data sets that were never seen by the model during training, and also on tasks that were never seen by the model during training. And we have seen great generalization. So what is super remarkable here is that a pre-trained model is taught to reason over any database for any predictive task. And I know this is a lot to believe in. It's kind of crazy that it's even possible. But it's been validated by a number of different organizations on their private data that Kumo never had access to. So that is very important, and in those use cases, the model performance came on par, and many times it was more accurate than manually built models using tree methods or neural networks that were trained and supervised and developed over months and years. So that's the kind of the magnitude we are talking about. In terms of the API and SDK we are making available, if you want to play with this for free by yourself, the SDK is then sending your data to our neural network and back. If you want a more private solution, we can actually install the model in your cloud, in your virtual private cloud, and you can then use it securely. If you would like that, please fill out the form on our website, and our sales team can get in touch with you. So basically, what I'm saying is we have two ways to do this. One is through the public API. You just download it and you can start using it. If you want a more secure, more enterprise option, we also offer that. We can install it on your side. No data leaves your environment, but we need to do the installation and things like that. So that's what I wanted to answer. What we also offer is fine-tuning. So whenever you know your task and you want to truly get optimal performance out of that data, then you can fine-tune for even better accuracy. And that becomes very important for high-end, super important use cases. That's what I wanted to quickly explain. Now, Vid, you want to answer any questions?
Yes, I believe we got some interesting questions about, whether names of tables and columns are relevant and how language works. So at the moment, no, the RFM is operating on this sort of meta level of categories and number distributions. So the names of columns themselves do not matter at all. And same goes for names of, for example, categorical data that might appear in the database. This is particularly important because it also allows obscuring private information, and it will not affect the performance of the model. The final question, which was that is probably worth touching, if there is some particularly relevant textual data where some advanced text encoding is needed and some, I'd say, less common language is used, Kumo RFM can always operate on this raw embeddings, which can be provided with an embedding of choice. So to answer, yes, we operate. Most of the time we are language agnostic, but we can add, we also support language inputs if needed.
Yeah, great. Thank you, Vid. Disha, anything you want to pick up?
Yeah, I can go next. There was one question from Ruben on how do you deal with target leakage, especially if the data is distributed across several tables? Is this the part where the human input is then needed? So yeah, this is a great question and a very common problem in machine learning that as data scientists we encounter. So basically how Kumo is designed, it's designed to work with relational data, right? The predictive query design, the task definition, it takes care of the time semantics in your data. So if you have dates, it would define that the target window should be as such, and the historical window should be before that target window. So automatically using that, we are accounting for any information that should not be used from the future is not being used at training time. That's one aspect. If there are aspects which have silent leakage where you have some very specific definition and you've not specified the dates correctly, and that's the part where the human input would be required, where you see the data and you should be able to tell that, hey, this is a column that was the timestamp around it was set up incorrectly. So it's a mix of both, but the platform provides a lot of visibility and explainability around what's happening. So you will be able to see that if there is a particular column that is showing really high in terms of variation of prediction in the model, you will be able to see that maybe it's a leaky feature. So you'll have the tools for you to take a look at the model and tell that, hey, maybe this is something that I should be reconsidering and dropping from my training. So yes, we have guardrails around that in the product.
Thank you, Disha. I can address a few questions around in-context learning and also how is Kumo RFM different from what is out there? And the key difference is that when people claim they have, let's say, foundation models, either they are taking the sequence transformer and they are creating some user sequence or some transaction sequence and feed that through a pre-trained transformer to say they have a foundation model. So I would say that's one line of work that we see in popping out. And then there is, of course, the notion of tabular foundation models that are single table models, which means that you have to first do the feature engineering, table flattening. You have to manually create the target column, the target label, and only then you can use the tabular foundation model, right? So still you have to do 90% of the work of all this data crunching and munging, and then you can basically say, here's one table, please complete this column for me. What is different in Kumo RFM is that natively operates over a set or a collection of tables. So no data manipulation, no table flattening needs to be done. And it comes with a query language, so you can actually ask it questions directly to get predictions. These questions can be like, impute this column for me, but the questions can also be these temporal forward-looking questions. And that's a huge difference between what is out there. In terms of in-context learning, right? So the way the model operates is that it gets these in-context examples in real time. They get pushed through the frozen pre-trained model to get the response, to get the prediction. The prediction both has the value as well as has the accuracy estimate or confidence. And this means that predictions are non-hallucinated, but we actually know the certainty, the trust in the prediction that is being given. We see that especially with small context sizes where you don't have too many in-context examples or too much, let's say, training data, in-context learning works beautifully. We see in-context learning working really well up to about, let's say, 10,000 in-context examples. What is important to note here is that to put 10,000 in-context examples into the model, the number of tokens, if you think of this as tokens, let's say cells, that number goes in tens of millions. So the context sizes we are dealing with are far bigger than what large language models can do. Because we go from one table to the next table to the next table, and we kind of recursively expand this throughout the graph of tables. What is also then important is that our attention mechanism is not quadratic. Because if you are quadratic, let's say in 10 million tokens, it's impossible to do that computationally efficiently. So there is a lot of innovation behind this to make the model scale and perform so that predictions can be returned in real time. Of course, if you have billions, tens of billions of training data points, and you know the predictive question ahead of time, fine-tuning would be something one could consider to squeeze out the last percentage point of information. So if you are interested in evaluating this, as I said earlier, you can evaluate it with our public API that is free to use. We do not store the data that you will send through. We do not use it for training. but it goes through our GPUs. If you are interested in evaluating this on your private company data, please reach out and you can talk to our sales team and we can see if we can install this inside your premises to be able to use it. So this is what I wanted to say. I think, Vid, you want to go next?
Yeah, I've got one very practical question here. They would like to know, how clean the data should be ahead of time. So we have trained Kumo RFM to be robust towards perturbations, towards null inputs, towards duplicated keys and all of that. And you can find ablation studies for different percentage of missing data and noisy columns and similar in our paper. So the answer is the model should in principle work, but obviously there is a limit to everything. You cannot expect to dump in a completely noisy data set and guess and have the model guess the right answers.
Yeah, maybe I can add what we see for the model is that it works really well with incomplete, noisy data. Because of this relational context that is provided, we observe that the attention mechanism is able to much more robustly extract signal from the raw data than these manually engineered features. And that's what we have. That's what we have in the paper. That you can check those experiments. And we see that this especially, for example, is important for this kind of cold start problems, new types of items where the information is very scarce. So this type of approach really excels in this type of noisy type of data.
I can go next. There are a lot of questions around evaluating model in production. So, and evaluating Kumo. So I'll address that. Jure has already touched upon it a little bit. But if you were to evaluate relational foundation model or Kumo's fine-tuned version, the approach is that you would connect your data with these models, and we reach out to us. We have secure ways of doing that. And then what the approach looks like is if you have an existing model, we could do a comparison of our outputs with that, come up with an evaluation framework, and that comparison would show what it looks like. But in addition to that, there are several other things to consider when you think about evaluation, and those are the time that the model saves. Typically, we have all seen it takes months and months of effort, feature engineering, pipeline maintenance, and all of that to create a model like this, which answers just one single problem. But with a framework like this, you could fail fast. You could try several things, bring on your relational data and answer several questions and see how you can really quickly answer some of these important business questions. Cases where you see that you absolutely need the models that are very complex and the questions that are very complex, and you absolutely need to fine tune all your data. It's really easy to even do that with Kumo's fine tune offering. So we have frameworks to help you evaluate the model first, gain the trust on what you're trying to do and how the model is doing on that. So yes, if you're interested in that, please reach out to our team, and we would be able to help you with evaluating on your own data set.
Yeah, I can answer one group of questions, which is about the schema. So the foundation model needs access to the set of tables and needs to understand how these tables are connected among each other, what the pointers are between the tables. Now, a human operator can register these things ahead of time. Kumo model can connect to the semantic model that many organizations have and extract this information directly from the semantic model. Or our agent is also able to basically crawl the database and extract this information. Then the human expert can verify it, and then the querying is possible. But it is, there are different ways to bring this information into the model. What is beautiful about the model is because it's schema agnostic, schema can keep changing over time, and the model will still work. And it's actually very important that when we pre-trained the model, we actually taught the model how to deal with noisy data, how to deal with irrelevant data, how to deal with irrelevant tables, irrelevant columns, and so on. So the model knows how to attend and extract the signal, even though information is noisy, spread across multiple tables and things like that. That's kind of the key part of the pre-training to really teach the model how to learn from noisy data. I mean, in terms of, I'll answer another one. In terms of model performance, right? The way the model performance is measured, it's measured in kind of in the same way as any AI, predictive or generative model performance is measured, right? You have a golden set where you know the set of true labels, and then you let the model predict those true labels, and you can compare the discrepancy between the prediction and the truth that is hidden from the model. So this means you can, for example, if you are running the model on live data, you can always see what the model predicted, what the true outcome was, and this way you can monitor, trace the accuracy of the model over time. What is beautiful with the foundation model is it doesn't really need to be retrained. And as the underlying schema changes and as the underlying data patterns change, the model naturally adapts to it. And we've seen, for example, great successes, especially in fraud detection domain, where it's a very adversarial problem where the fraudsters are always figuring out how to get through, but the model discovers them quickly, figures out those patterns, and makes robust predictions going forward without any human manual engineering of new features and trying to catch new fraud patterns. The model kind of does that just automatically.
I've got another question here asking about the model heads, given that fairly diverse problems can be specified in predictive query language, or does the model dynamically use a different model head? And the answer is yes. So one advantage of using this predictive query language is that we can infer the task type and adjust the model head accordingly so that the right model head, or the right approach is used to best answer a specific query.
Okay, so we reached the end of our workshop. Jure, Disha, and Vid, do you want to cover one more question maybe? Okay, so thank you again, Jure, Disha, and Vid, for sharing your knowledge and all practical examples. And thank you, all of you, for joining and for your amazing question and positive comments in the chat. For any question we don't have time to address live, we will follow up via email. I hope you gain valuable insights. And tomorrow we will send you an email with the video recording and all important links that we've mentioned during the session. Thank you once again for your time and attention, and have a great day.
Thanks, everyone.
Thank you very much.